Thank you. So let me start by thanking Ajit and other organizers for the invitation, and of course ICTS for hosting us. So what I am going to kind of briefly touch upon are some of the interesting questions which I think is important for cosmology, as well as some of the upcoming frontiers, which again is biased by my choices, but I think it will have very interesting consequences for future gravitational wave observations as well. So the connection between gravitational wave and cosmology is now very well known. Almost all kind of gravitational wave probes have some connections to cosmology, and this is a slide I picked up from the Nanograv collaboration, which basically brings this out quite nicely. Starting from ground-based interferometers, where if not now, but probably in the future, we will have sources at really cosmological distances. I mean, we are already having, but I'm talking about really a large number of sources at very high redshifts, which will come up with the next generation of ground-based interferometers, most likely. The space-based interferometers like LISA will be probing black hole mergers at high redshift. Same thing with pulsar timing arrays. I mean, we are talking about stochastic background of gravitational waves, which again, the probe is happening as we speak. And CMB B modes, basically the polarization signal from CMB, which is going to be, I mean, if detected, is going to be an excellent probe of primordial gravitational waves from inflation. And many of these topics will be touched upon or may have already been touched upon in the earlier days, and I'm sure will be talked about in the subsequent lectures. The talk outline which I had in mind was that I will start with some ideas about successes we had with the present concordance lambda CDM model, but then what are the challenges we are facing in working with it. And then I will move to something which is relatively unexplored, that is the high redshift universe, and that is being like coined as the next frontier of observational cosmology. And one specific example related to this high redshift universe is the JWST revolution, which I will spend some time, and I think it has some lessons for us to learn in doing cosmology with new probes. I think it will have some implications for gravitational wave cosmology as well. And of course, that will lead us to talk about synergies between gravitational wave cosmology and the high redshift universe. So lambda CDM, I mean, no matter how many challenges it is facing now, it's a really successful model. And that's why we are finding it very difficult to let it go. It kind of agrees with a wide variety of observations, and its parameters have been kind of measured to a very high degree of precision. And some of the probes which have really helped us in shaping this concordance lambda CDM models are the so-called supernova 1A, which gave us idea about the fact that the universe is accelerating. Of course, the CMB, which kind of cemented this lambda CDM paradigm, so to speak, and then galaxy surveys, or in general, the large-scale structure. So when you combine all these different aspects of all these into a form, we have a very nice model which tells us different energy components of the universe and how it's expected to expand, and so on. So this is the model which we think we are happy with, and most of the time we keep on working on. However, I mean, there have always been open questions within the model. So often the joke is that the lambda CDM model is very nice, but it has only two problems. One is lambda, the other is CDM. So we don't know, basically, we don't have much idea about any of these two components. So first is the dark matter. I mean, we probably know it's a collisionless cold component, but we don't know how cold it is. What are the particles which are giving rise to the dark matter? The dark matter aspect is probably best probed by the matter power spectrum, which has been plotted here as a function of wave number. So these will be small scales and these are large scales. And this basically shows the data coming from a wide variety of observations. For example, CMB at large scales to galaxy surveys at intermediate scales to lensing and Lyman alpha forest at very small scales. And this is the prediction of our concordance lambda CDM model. And you can see it matches a wide range of length scales quite well. But nevertheless, so even if we believe that this part of the cold dark matter or the dark matter paradigm is reasonably well settled, that is the intermediate to large scales, there can still be questions asked about what happens at really small scales. And that is related to what is the exact nature of dark matter. Is it still WIMP? Are we okay with that? Then why aren't we detecting them? Or is there scope for making the dark matter particles a bit lighter than what we thought, the so-called warm dark matter model, or maybe it is some axion-like particles self-interacting, and there are various other choices. And the hope is that at some point we will have some access to very small scales here, and hopefully we will be able to distinguish between these options. The other is, of course, the dark energy part, and at this point we are not even sure whether it is lambda, that is the equation of state being -1, or it is something not equal to -1 but constant, or is it kind of evolving. And this is something which has become, I mean, all of you would have seen the latest results from the DESI collaboration, which seem to indicate that not only the dark energy is evolving, it is behaving like phantom at high redshifts. So what, for example, if we look at this equation of state plot versus redshift, this is how it looks like, that at low redshifts it's not equal to -1 but greater than -1, but at high redshifts it just goes below -1, and this is something people worry about. Now, there are various questions to be asked about how much of this is an artifact of the parameterization you have chosen, and are there still like systematics to worry about in the data, and so on. So this is something which hopefully will get settled, but still it will only tell us how dark energy probably evolves with the redshift. What it is still an open question, and I don't have an answer as to how we will answer it. And then, of course, there are other questions which have been plaguing the lambda CDM model. For example, at what point do we think that inflation is a settled issue, that's a paradigm we trust and we have tested, and so on, and similar other questions. But these questions, remember, what was at a stage that we can measure all the parameters to a very high degree of precision. There is some lack in our understanding. So we have to just go and try to understand all these components. What has hit us in the last 5, 7, 10 years are more serious challenges, and these are usually called the tensions, and the most prominent and the most probably severe of them is the H0 tension or the Hubble tension. So here the idea is that you are measuring the quantity, which is the expansion rate of the universe at the present epoch, and when you measure using different methods, particularly a set of methods which depend on this local distance ladder versus a method which relies on CMB plus lambda CDM model, you seem to get different answers. So what has been shown in the left-hand plot is how these constraints on H0 evolved as function of year of publication. And this tension was showing up somewhere around 2010, but even at that point, the error bars were large enough for us to kind of not worry about it. But this has become a really 5 sigma or more tension in the recent days. If you compare the blue one, which come from CFIDs being used as the local distance ladder versus CMB. Now, unfortunately, the story is not that simple. It's not that we have a simple bimodal kind of measurement of H0. There is another set of measurements which come from so-called tip of red giant branch. And that seemed to fall bang in between. Remember, this is also, conceptually, it is based on something like distance ladder. So what is going on is something which we don't understand. Why isn't it matching with the CFIT based measurements? And then when you plot, so what has been shown in the right hand plot is basically the H0 measurements from different individual observations. And the claim is that even now, we really don't see a bimodality. They're kind of all over the place, with CMB and the CFIT being the two extremes. So there is clearly something going on which we don't understand. And this is something which hopefully will be settled in the next few years. So, one way of looking at it is, before really going and really kind of throwing lambda CDM away, or basically trying to make non-trivial adjustments to it, maybe we can wait for the CFIT TRGB systematics to get resolved first, so that let's see what's going on here. But then the question is, are there still unmodeled astrophysics, maybe metallicity dependence, which hasn't been properly taken into account while calibrating the CFITs, and so on. What are these? These are basically different H0 measurements coming from, these will be like one paper, let us say. Unfortunately, they are not color coded, so it's not easy to tell what method has been used. But what you can understand is this lower part will be CMB kind of a thing. These are shoes, which is clearly indicated, and the middle one will be other kind of, mostly TRGB and related stuff. They also don't show the error bars, so it's not very easy to understand. But the point this Wendy Friedman and their group are making is there is no bimodality. So there's something else which is happening. It's not like two sets of observations are measuring two different values. It's more than that. It turns out that it is not, even when, if you stick to lambda CDM, it's not very easy to resolve this tension. People have played with early dark energy models, but given all other observations, and if you want them to kind of stay where they are, it's not very easy to resolve this. You can alleviate the tension to some extent, but it's probably not going to go away very soon. Of course, there is still a possibility of observational systematics, but with depending on who you talk to, they always believe that their measurements are solid. And this is where, of course, I'm sure you have already heard about it, that the gravitational wave cosmology has already started playing some part in it, in the sense it has started showing some promise. And this is that famous merger event from which the H0 was measured. So at this point, the error bars are much larger. Of course, you can refine it by making more assumptions about how this source behaves. And I'm sure we will hear about how these H0 measurements are done using different gravitational wave observations, and what are the promises in the future. But this is something to keep in mind. Of course, after this event came, there was a lot of excitement in the community, and people went ahead and tried to calculate how many such gravitational wave electromagnetic counterparts, so-called bright sirens, you would need to really nail down the issue. And the numbers which were quoted were somewhere around 50 or so. Once you have that many events, you will measure H0 to the accuracy as the other observations are doing. And the hope was that we will have such events in the next few years during those days. Unfortunately, that hasn't happened. But that doesn't stop this field, because you can also do a lot with dark sirens, which are being detected all the time. Here, of course, you have to take recourse to a statistical method, or you have to probably cross-correlate with galaxy catalogs. But it is possible. And again, I'm hoping that we will hear more about these things in the subsequent lectures. Going beyond simple number counts or distances, you can do a lot more if we measure the distribution or the clustering of gravitational wave sources. So here you are really doing, you are measuring the large scale structure using gravitational waves. And again, this field has evolved a lot, and the results I'm showing is from something which we had worked on quite some time back. And the idea was to see at what point will we be reliably detecting this clustering signal using the 3G network detectors. And it was quite promising given the calculations we had done at those stages. At that point, we were talking about measuring the bias or how these gravitational waves are clustered relative to the underlying matter distribution. But in general, if you are measuring clustering, then you are basically accessing a lot more information about cosmological parameters, and it may have implications for other tensions which we talk about in cosmology. For example, the so-called S8 or sigma 8 tension. This tension, again, depending on who you believe, is probably not that severe, so I'm not going to really talk about it, but we can discuss if time comes. And then once you move to this structure formation kind of paradigm, then a whole set of other kind of possibilities open. Now we are talking about lensing of gravitational wave sources, using them, maybe cross-correlating with large-scale structures, and again, the idea would be to go and measure cosmological parameters. And it's not necessarily only related to the parameters which are interesting for tensions, but in general. I mean, you can go and, for example, measure the dark energy equation of state, just like DESI and other large-scale surveys are doing. And then again, you have an independent way of looking at dark energy and so on. What I wanted to move from here is what next? I mean, this is where lambda CDM is. There are challenges, there are successes, and we have to wait for more data to come, more analysis to be done. But there are a couple of frontiers which are still not kind of touched upon and will probably open up in the next few years. One is the so-called dark ages. So what has been shown here is some kind of a broad timeline of our universe and some of the interesting epochs as far as structure formation is concerned. So one part which we use for doing large-scale structures is CMB basically, which shows all these very nice small fluctuations which tell us that tell us about, for example, the primordial power spectrum, its slope, its amplitude, and so on. And the other part where we do large-scale structures are the galaxy surveys, which appear in relatively low redshifts. There is a phase which is relatively unprobed, and this is kind of gradually being probed. I mean, JWST and in the future various other telescopes will go and probe this regime with lot of confidence. And this is the regime where the first stars or the first galaxies in our universe formed. Now we don't know when they formed. Was it redshift 15, 20? And how did they look like? What were their effects on the subsequent galaxy formation? Are things which we haven't answered yet. And this is where observations would really help. And I will spend some time on this. The other unprobed frontier, which I talked about, and you will probably hear a lot in Sriram's talk, is the B modes for primordial gravitational waves. And so going to the high redshift universe, so as I said, this is currently being probed by a wide variety of observations, and I have just shown a few, starting from optical UV to very kind of low frequencies, that is radio. So here one is using quasar absorption spectra to probe the high redshift universe. JWST is probing the high redshift galaxy. CMB anisotropies probe effects of these first stars through secondary anisotropies, and this 21 centimeter signal from neutral hydrogen is something which is happening now, and it will improve a lot in the next few years. And using these multi-wavelength high redshift observations, we hope to learn a lot about galaxy formation, properties of early galaxies, feedback processes, how did the chemical enrichment happen. So that will tell us about what kind of stars were forming, what were the nature of the first stars, for example. And in principle, you can also do cosmology. You can try to learn about halo mass functions, the properties of the cosmic wave. And if you are lucky, we may be able to do like constrained non-standard extensions to the lambda CDM, or maybe detect some of them. So this brings me to something which has become extremely exciting in the last like 2-3 years. That is the data we are getting from JWST. And this is just one way of showing it. So what has been shown here on the top panel are basically galaxies which are being detected. The y-axis shows you the luminosity, and this one, the x-axis, is the redshift. So the blue points are the galaxies we had detected before JWST came up. So this was, for example, the HST era. And you can see the blue dots are, firstly, they are sitting at relatively lower redshifts and towards the brighter side. So we were mostly detecting brighter galaxies with HST. But once JWST came up, you can see this kind of plot completely changed. Not only we are detecting galaxies at really, really high redshifts, we are really talking about redshifts of 14 or so. We are also detecting galaxies which are faint, and we believe that population is usually dominated by a large number of faint galaxies, and this is something which we are going into. This is good, but once we started detecting these came up with their own puzzles. For example, if I plot the star formation rate integrated over all galaxies versus redshift, these are, for example, the points. So the blue points were during the HST days, and these are coming from JWST, the orange ones. And if you just use something which we have been using so far, a galaxy formation model which was okay, a good match to the HST observations, it seems that the JWST data give larger or higher amount of star formation rate, or maybe more galaxies than what we thought we would get. And that was a kind of surprise. Now that gave rise to the question that are we now looking at something where lambda CDM can be challenged? So if we look at the solutions, there were kind of two kinds of solutions which people were worried about. One is that you change the matter power spectrum. You put some excess, making sure that you are not really violating any of the existing constraints. So the idea is if you put power in some scales which you would like to, you may be able to form more halos at high redshift and then hence produce more stars. The other option is more geometric. You say that you come up with a way to change, let's say, the growth rate or the expansion rate of the universe at high redshifts. Now that will change what the growth of structures as well, and through that probably you go for find increased abundance. So we thought that we will take a look at both examples of both these cases and see what happens. So to study a model which gives rise to excess power and hence more number of halos at high redshift, we took a case where there is, for example, a primordial magnetic field. So primordial magnetic fields can help generate, for example, power at extremely small scales. So this was done making sure that the power spectrum plot you saw with all the data points put in, all those are respected. And what has been plotted here is the halo mass function, so the abundance of halos versus mass. The dashed line is the lambda CDM, whereas this one comes when you put some magnetic field. And you can see indeed you are producing more halos. Now what we do is then we vary the parameters of the magnetic field, the primordial magnetic field, mainly its amplitude and the slope of the spectrum, as well as the astrophysical parameters, keeping the astrophysical parameters related to galaxy formation fixed, in the sense they don't evolve. They can vary when we actually do the parameter estimation, but they don't evolve, basically. So that is the assumption. So the question is, can primordial magnetic fields explain the JWST excess? So this is a plot which shows the luminosity function. So again, this is the abundance versus luminosity at a wide range of redshifts, from redshift 5 to 13 or so. Black are the data points. The dashed is the lambda CDM prediction. So you can see the lambda CDM prediction, it matches, it agrees with the data points up to redshifts of 10. And after that, the lambda CDM tends to kind of fall below the observational data points. This is another way of showing what I showed you earlier through the star formation rate plot. Unfortunately, the primordial magnetic fields, they tend to alleviate the tension a bit, but they are not going to solve it. And if you go and try to understand why this is happening because we have a lot of data between 5 and 10, and we had a reasonable amount of data during the HST days also. And this data, I mean, if you want to fix, you know what kind of parameters these data want. I mean, these data points are okay with standard lambda CDM and so-called non-evolving astrophysical parameters. So most of the things gets fixed by this part. And now you have to find a way to somehow change the model beyond redshift 10. So it's like nothing should evolve to redshift 10 and then you start evolving above redshift 10. And that becomes very difficult to do with cosmological solutions. I won't go into details, but we tried the same with a different early dark energy model, and we came up with a similar conclusion, that it is not very easy to solve the JWST excess by only cosmological kind of effects, keeping the astrophysics completely unchanged. If you go to the other extreme where you say that we believe in lambda CDM, but let us now play with our astrophysical parameters, the game changes completely. So this shows after fixing these parameters by matching with observations, what kind of models are kind of allowed. So what has been plotted here are different astrophysical parameters versus redshift. So if you look at, for example, this parameter is a combination of how much baryons or gas is converted into stars within galaxy, multiplied by something which depends on the initial mass function of stars. So the idea is this is the quantity which converts the gas to stars and from there to UV radiation, which you will observe in JWST galaxies. And you can see this quantity is reasonably constant till redshift 10. As I said, this is what the data demands, and this is why we didn't need anything to really evolve before JWST came up. But above redshift 10, you really do need some evolution. Okay, and we know now what kind of things evolve, and of course, I mean this matches the EV luminosity function data over the full redshift range, which I was talking about. I'm not going to show, but it also does match several other data which is coming out of the JWST. For example, JWST is now measuring clustering of high redshift galaxies. So if you have a model which matches the luminosity function, doesn't guarantee that you will match the clustering as well. And this was really a lesson for us as well. And then once we went ahead and took the clustering data into account, I mean, many of these things fell in place. So currently we think that lambda CDM is probably not under threat from the JWST excess which we have been seeing. It is the astrophysics which is driving, and it's probably we are looking at very different kind of galaxies, the so-called early galaxies, probably the metal-free galaxies which are occurring at these high redshifts. But we need more observations and more individual galaxies to be observed once to settle this issue. So this is basically the lesson which I think is important, that in principle new observations can be used to constrain cosmological parameters, but you have to be always wary about the astrophysical part, and that now is showing up in various cosmological calculations as we see. So this idea about doing cosmology without worrying about the astrophysics of galaxies is probably not going to work in the near future. We have to kind of make sure we understand both of them simultaneously. The future in this field is the 21 centimeter observation. So in this case, we are not going to go and observe the individual galaxies, but the effect of galaxies on the surrounding neutral hydrogen. So what has been shown here is a simulation which we have been doing. This is the neutral hydrogen distribution. So red ones are neutral, black is ionized. So as you form galaxies, you will see you form these ionized regions which kind of grow, percolate, and eventually the whole universe gets reionized. So that is reionization. And the hope is to detect this neutral hydrogen signal. This is different from detecting individual galaxies, because when you do individual galaxies, you are most likely to be biased towards the brighter ones. So there is a luminosity bias which kicks in. In this case, neutral hydrogen will be affected by whatever is the representative population at that given epoch. So in that sense, this is kind of more democratic, so to speak. Now, where does gravitational wave come in? So gravitational waves come in various waves while discussing high redshift universe. Firstly, if we are talking about CMB kind of primordial gravitational waves, it is possible that this neutral or the ionized universe can play some kind of a spoil sport or act as a contaminant, because these patches, this patchy neutral hydrogen or ionized distributions can also generate B modes. Now it all depends on what is the amplitude of the B mode signal vis-a-vis what is the power in this reionized patchiness. So that is something to think about. The other thing is gravitational wave observations will tell us about the properties of first galaxies. It can be that these first galaxies, wherever they are forming, will also eventually form the supermassive black holes and their merger will be detected in LISA, for example. Or in general, the star formation rate happening in these galaxies will reach to the standard stellar merger kind of events, which will probably be detected in the upcoming 3G detectors. So this is the kind of picture I want you to have in mind. So suppose you have cosmology, in particular the halo mass function. What you need is, within the halos, you will form stars, and that will depend on various, like gastrophysics, so to say. So you will have to put cooling, feedback, and various other things which go in. Once you have an idea about how star formation is happening, you can calculate the UV property. So these are the kind of properties which will be observed by a probe like JWST, and that is what is happening. And going from star formation to UV properties will also depend on what kind of stars you have formed, what is the age of the stellar population. If you now want to do 21 centimeter, that is happening because of the intergalactic medium, the hydrogen in the intergalactic medium. For that, you need to do a bit more. I mean, you have to now say that I'm not worried about really the UV photons, but the ionizing photons. How are they escaping from the galaxy? In addition, the H1 distribution may also depend on the Lyman alpha radiation and X-ray photons. So you may have to account for all of these. Sometimes people don't worry about this part and just go from SFR to H1 distribution, but you still have to worry about all these. Now, what happens is, if you want to study either one of this and try to understand SFR or try to do cosmology, you can see there will be all these processes which are sitting there, and often you may not be able to distinguish a cosmological effect from many of these. So it is best to have multiple observations, multiple probes to break some of these degeneracies, and that is where the gravitational wave events can be extremely interesting. Now, you can relate the gravitational wave events also to the same star formation in the galaxies. Of course, you will come up with different kind of astrophysical systematics there. Now you have to worry about the delay time distribution, the probability of merger, and so on. And keep in mind that the high redshift universe can be very different. This picture may hold in at every redshifts in general, but all these processes will be very different at high redshifts compared to low redshifts. So that is something to keep in mind. So the usual insights we have at low redshifts may not be very easily extrapolated to the high redshift. And this is where we were playing with a proof of concept, a project which is being led by Avinash Tiwari Nayuka, which I think is here. So what we were trying to do is whether we can use 21 centimeter and gravitational wave synergies to tell us something about the properties of these galaxies. So the idea was that you generate a mock 21 centimeter signal, which is shown here, and try to constrain the properties of the galaxies. So this is what has been tried here. What turns out that various parameters are completely degenerate. This is partly because of the simplistic model we chose, but the basic idea still remains. Okay, you cannot distinguish star formation rate and, for example, the Lyman alpha efficiency or the X-ray efficiency, and that shows up in these panels. Okay, that the parameters are not at all constant. The moment you inform these observations with some gravitational wave events, you can see the degeneracies break. So we have a proof of concept which we are working on, and it's already showing some promise, and this is something to think about. So I'm almost done. So as the future is really bright in synergizing high redshift universe with gravitational waves. So this is a regime which is relatively unexplored, but it holds a lot of promise. So SK will come up in the next few years. So will be the extremely large telescopes. And in the gravitational wave side, hopefully the space-based and the upgraded ground-based detectors will be in place. The only thing we probably need to worry about is that the timelines may not match. I mean, these things will come up in the next 5 to 10 years, whereas these things probably will take some more time. So, but one needs to probably think about how to do the synergy. So I will leave with the summary slide, and yeah, thank you very much.
Thank you very much, Tirth, for this very clear overview and for not leaving astrophysics out of cosmology also. We have several questions. We'll start with Bruce.
I have two questions.
Yeah.
The first considers is about equations of state with W less than -1. So many years ago, Rob Caldwell wrote a paper about the big rip. What happens if going towards the future, W is less than -1?
Yes.
I wanted to ask you what it means going to the past. That's my first question. And the second question is, I'm confused about how you can study cosmological structure using black hole mergers. The reason being that we know that there's about 30 of those in a year per cubic gigaparsec. So the average distance between them is several hundred megaparsecs.
Yeah.
So you're dominated by shot noise. That's too far apart to see the structure. Yes. So those are my two questions. Thanks.
Yes. So this is something we tried to work out, and maybe, I don't know if Adhya is around. Where we really put in the effects of both short noise and the uncertainties in your localization in the calculation. It's just that you're beating the whole thing by a huge number of events when you integrate over between 5 to 10 years using the 3G detector network. So this is a really far future thing.
I see. So I guess if you wait 10 years, then maybe the average distance.
Exactly.
You can maybe start.
Yes. Yes. So that is the idea. Yes. So this is somewhat in the.
But shot noise is a problem. You're fighting shot noise.
Yes, but they will. So if you assume the short noise to be kind of flat, I think they will affect the small scales more than the large scales. So hopefully we will still be able to do cosmology at large scales. The other part, I really don't know. I mean, I think let's wait for this. Yeah, this thing to settle down. Let's not really. What I wanted to show is there is still a lot of excitement in the field, but I will wait for some more time. Yeah, I mean, okay. I mean, clearly this is not a model which can be described by, for example, quintessence, simple scalar fields and things like that. So we are going beyond that. Yeah. But remember here also the dark energy fraction is also going down. So the universe may still be quite dark matter dominated, but we can discuss. Yeah.
Very nice talk, Tirth.
Thanks.
So you mentioned these sort of cosmological and astrophysical ways of explaining the JWST. And for your cosmology part, I somehow kind of got the impression that you are saying a bit strongly that the cosmological explanations are not viable to explain the JWST. But I believe this is just, let's say, one particular modeling of the enhancement of the power spectrum. There are actually some papers on early dark energy, not necessarily in the context of explaining the Hubble tension, but at later time.
Yeah.
okay, some evolution in the dark energy equational state, which actually can also provide explanations to the JWST.
So we should talk about this. So we actually explored a wide variety of models there. The problem is the moment you make sure that everything is consistent with CMB and other experiments, you are left with, for example, a very small amount of parameter space. But more importantly, what the data likes is something which does not evolve till redshift 10. And after that, it starts evolving.
I see.
Tuning that becomes very difficult. So what often people do is people just take a particular redshift where JWST excess is extremely strong, let's say redshift 13 or 12 or something, and they show that a cosmological explanation is good enough to match that. But if you now extrapolate it to lower redshifts where we already have data, they will find difficulties. And that is a generic statement which we are seeing. Okay, I still agree that probably the statement was too strong. There could still be some, but we haven't seen such an possibility which really explains everything just from cosmological arguments.
Okay. Yeah. And the second part of the question was on the astrophysical side. Yeah. So you mentioned these, high star formation scenarios which could give rise to.
Yes.
So what about, and you also made a statement that these are the early galaxies with low metallicity.
Probably. Our model cannot
Can we
distinguish.
think of early galaxies with high metallicity? They will give rise to a larger star formation rate because the baryons will cool down quickly.
Yeah.
Okay. And then
So
that can give rise to...
I can answer. So our model, okay, it's not a first principle based model. So it has parameters. This parameter is a combination of how much stars you are forming times this top heavy IMF. Okay. So what you can say is that I will keep the IMF same or full of metals and increase the star formation rate. That is fine. Or you say that the star formation rate remains the same, but I will make them IMF top heavy. So both will work in this case. And at least what we show is they are completely degenerate. This degeneracy can be broken by what we call stellar mass function observations. I did not show them, but yes. Again, those observations are still at very, because there you need spectroscopically confirmed galaxies. So it's difficult. There are less number of data points, but one can do that. So JWST is a fantastic experiment in that sense. Yeah.
Shmudeep, could you wait for the panel discussion? Is that okay? Yeah, thanks.
Yeah, thank you for this talk. I found it very interesting. At the end, you had the study combining 21 centimeters with gravitational waves. I'm wondering where your black holes are going to show up in the gravitational wave frequency band. What properties of the black holes are you assuming, and what are then the detector frame masses?
Sorry, what the?
And what are then the detector frame masses at this?
Yes. So these calculations are done keeping the upcoming 3G detectors in mind. And also, I mean, this is a very simple model where we have kept the black hole mass fixed to some number, which I don't recall for the moment. They will, of course, fall in the appropriate frequency band. So that is not a problem. We have also not played with, for example, the delay time distribution. This is just really a proof of concept model. But in principle, you can make this work because you will have a lot of 21 centimeter as well as this data. And the idea would be to now jointly model both of them and try to fit both their parameters at the same time. And that is something which we haven't done, but yeah.
The black hole properties should also change with redshift, shouldn't they? The probably ones be heavier, I believe.
Yes. And probably, yeah. All the delay time distribution could be, delay time could shrink if they are heavy. None of these have been explored here. And that is why I said this is a really open and unexplored field, which is like asking us to go there and explore.
I know there are many questions. I suggest that you add them to the Google Doc that I circulated yesterday, and we'll take that in the panel discussion. In the interest of time, let's move on. Let's thank Tirth once again for this very nice talk.